All right, so we first came across matrices um, as a result of building them from systems of equations. But matrices are mathematical objects in and of themselves and are used in a lot of situations separate from linear equations. All right. So what we want to look at is in 3.4 is just the idea of matrices, at least initially, just as mathematical objects. Okay, so we just want to take some matrices. They're not tied to any systems, um, and do some and look how we work with them. Consider how we work with them. So let's take two matrices. All right, so here we go. And so what we want to do, if these are mathematical objects, then we want to be able to do the most basic mathematical things with them. So for instance, I would like, there's nothing more basic than addition, right? We're talking the basic operations here. So how do we add two matrices? If I want to add A to B, we get a new matrix called A plus B, and here it is. 3 plus 4 is 7. 0 minus 3 is minus 3. Minus 1 plus 6 is 5. 2 plus 9 is 11. Negative 7 plus 0 is negative 7. 5 plus negative 2 is 3. So what you get there is, if you want to add matrices, you just add corresponding entries. 3 plus 4 is 7. 0 plus a negative 3 is negative 3. And there you go. Right? Doesn't get much easier than that. Of course, your technology can handle this as well. But we want, we need to be able to do it by hand as well. So then if we look at subtraction, subtraction happens the same way, thank goodness. The new matrix A minus B is just going to be the corresponding A entry minus the corresponding B entry. 3 minus 4. 0 minus a minus 3, right? So that's going to become 0 plus 3. Minus 1 minus 6. 2 minus 9. Minus 7 minus 0. And 5 minus a minus 2. And there we go. Now, implicit in all of this is that in order to add or subtract matrices, you have to have matrices that are the same size. And so this is a 2 by 3 matrix, this is a 2 by 3 matrix, and so you can add and subtract them. That's obviously necessary so that you can add and subtract the corresponding entries. If they are different sizes, they can't be added, right? Somebody comes up to you with two matrices of different sizes and asks you to add them, you tell them that is undefined, right? So addition and subtraction. The other kind of third basic operation that we can look at is taking a matrix and multiplying it by a number, or what we call a scalar. All right, so just 3 times the matrix B, and this is going to happen just like you'd probably predict. You just do that term by term. 12, negative 9, 3 times 6 is 18, 3 times 9 is 27, 0, and negative 6. So we can multiply, and of course we can combine these things, right? Take 3 times A minus 7 times B. You would do the multiplication first and then add. All right. Let's move on to other matrix operations. We want to talk about let's talk multiplication, because multiplication, the simplicity that we get with addition and subtraction, we pay for in matrix multiplication. All right, so we get a little more complicated. Now to start this off, what we're going to do is we're going to deal with multiplying here. Let's take a what we call a row matrix. Okay, so we'll and that should be bold. Okay, so if I could write that bold, I would. But a row matrix is just a row. Okay, it's just a matrix that has one row in it. Okay, then we have a column matrix, which is just a matrix made up of one column. We start with, to understand matrix multiplication, we start with these two things: a row matrix and a column matrix. Now these these are kind of clunky words to call them row matrices and column matrices. We'll often refer to these as vectors, and we'll get into these a little later. Okay, so we'll get into vectors a little bit more. But let's just talk about how do we multiply a row times a column. It's a dot product, if any of you guys remember that from Calc 3. You basically take the first entry times the first entry, right? First times first. Then you're going to do second times second, right? Plus second times second, plus third times third. Oops, let's switch that. Third times third. Okay, and then of course you're going to add, so then you add those up. And so we end up with 1 times 4 plus 2 times 5 plus 3 times 6. So we end up with a 32. All right, and that's it. That's how you do a row vector times a column vector. It's a dot. It's a dot product. But first times first, second times second, third times third, and then add the results. Okay. Now we're setting all this up so that we can look at how to multiply matrices. All right. So the problem with multiplying matrices is that it looks fairly complicated when it's written down in a textbook. Okay, and it is kind of complicated, but in order to describe it, using text, you have to really rely heavily on subscript notation and things like that. All right, so I'm not going to dig into that. I'm just going to give you the example, and we're just going to look at how this is done. So let's take our original A matrix, which was 3, 0, minus 1, 2, minus 7, and 5. Okay, and I'm going to multiply it by a new matrix. We'll call it C, and it will be 1, 3, 7, 4, 8, 0, 5, negative 2, 1. Okay, and so here's the deal. I can actually multiply these matrices even though they are different sizes. Okay, there's a rule. How do we know when we? In fact, I cannot multiply the original A times the original B. So the first thing you've got to do before you can multiply two matrices is run a little thing that I call the size test. Right, the sizes have to match up. Let's see if we can do this. Oh, we can almost do it. I didn't carefully grab. Okay, so the sizes have to match up. So here's the size test. If you're going to do A times C, order matters. All right, A times C, order matters in matrix multiplication. Matrix multiplication is not commutative. All right, so if you're going to do A times C, you first write down the size of A, which is 2 by 3. And then next to it, you write down the size of C, which is 3 by 3. Okay, and here's what you're looking for. These two inner numbers have to be the same. If they are the same, you can multiply the matrices. It does not matter what the other outside numbers are. The first two matrices, those inside numbers have to be the same. Okay, so we can multiply these. Why couldn't I do the A times B? Well, A times B, just looking back up here, A times B would be, there would be a 3 and a 2, different sizes. Okay, so what we're saying by this little test is that the number of columns, and I always get this confused, so that's why I just rely on the size test. But what we're saying is that the number of columns in the first matrix has to equal the number of rows in the second matrix in order for you to be able to multiply. Okay, but I always get it confused. Is it columns in the first, rows in the second, rows in the second? So, but that's what it is. Columns in the first has to equal rows in the second. But if you just do the size test, if those two inside numbers match, then you're good to go. Now, as a bonus here, what do the outside numbers tell you? They tell you the size of the answer. So the matrix AC is going to be 2 times 3, or 2 by 3. All right, so I'm going to show you how to multiply these, and kind of pay attention to this because this method is not described in the book. They use a much more notational heavy method, which is not easy to follow always. So let's take our, I'm going to try this one more time. Why am I there? Let's just go that way. So let's take our A matrix and write it down. So this is how we multiply. And then kind of kitty corner to it, I'm going to take and write down the B matrix, or the C matrix. 1, 3, 7, 4, 8, 0, and 5, -2, 1. All right, so again, this is not described this way in the books, but I'm showing you this so that you can hopefully have an easier way to do it. Our answer is going to be right there. And look, our answer is going to have 2 rows and 3 columns. It's going to be 2 by 3. Okay, so that's great. That's what we want. To make that a little more clear, that means there's going to be an entry there, an entry there, an entry there, right? And there, there, and there. So we've got to figure out what those 6 entries are. All right, so here's how you do it. To figure out this entry, all right, what you will do is you will use this row and this column. See how those are the intersection of that entry? That row and that column. Okay, now the book goes in great detail and says, I'll write it down here. The book says if you want to find the A11 entry, which is this entry, you're going to use the first row times the first column. First row of A times the first column of C. And that's not that hard, right? First row times first column. But I can visually see it much easier. So I guess that makes sense, right? I can understand it when I see it laid out this way. So I'm just going to go this times this, and remember how that works when you do a row times a column. It's first times first, second times second, third times third. And so if we write that down, we will have first times first is 3, plus second times second is 0, plus third times third is -7. So 3 plus a -7 is a -4. Okay? All right, so let's move on to this row, which is going to use this row and this column, right? So we'll use the first row, but now we're moved on to the second column. All right, so we're going to go first times first, and again, first row, second column. First times first is 9, 0 times 8 is 0, -1 times -2 is 2. So that gives us an 11, and so that entry is 11. Let's move to this entry, which is going to be this row and this column. See how they intersect? And so when we do that, first times first is 3 times 7 is 21, 0 times 0 is 0, -1 times 1 is a -1, so that becomes a 20. Alright, now we move down to this entry, which will be this row and that column. Okay, that's why I lay it out this way, because I can always remember which row and which column to use. This, while technically correct, just sometimes confuses me. I mean, it's not that hard, but anyway, so let's go through and find this next set of entries. 2 times 1 is 2, -7 times times 8 is -56, and 5 times -2 is -10. So we add those. Did I get that right? 6, -56, and -10. So when we add those together, -66, -64. Okay, moving on to the next entry. 2 times 3 is 6. -7 times, you know what? This is the joy of live TV, right? You guys were all screaming at the screen, kind of like a football game, kind of like a live football game. Why did you do that? We're going to back up. This is wrong, right? Our little entry here is wrong. Let's try that again. I guess it's good that I caught it before I got to the very end. So once again, what are we doing? This row, this column, right? Okay, let's try it, but this time with correctness. 2 times 1 is 2. Negative 7 times 4 is negative 28. And 5 times 5 is 25. Okay, so 27 minus 28 is negative 1. All right, I hope that's better. Now, let's be clear here. This entry becomes this row times this column. So, to do that, 2 times 3 is 6. Negative 7 times 8 is a negative 56. There it is. And 5 times negative 2 is negative 10. I click that button. 6, negative 56, and negative 10. So negative 66 plus 6 is negative 60. Alright, last entry. This row, this column. So 2 times 7 is 14, negative 7 times 0 is 0, and 5 times 1 is 5. So that gives us a total of 19. And there we go. This is the matrix AC, and you can see that it is a 2 by 3 matrix. Technology can do this for you. Okay, you can enter A into the calculator or into GeoGebra and C in as well, and then do A times C and it will work. Now notice, C times A is not even doable, right? So if I ask you to find C times A, you would say that is undefined because it does not pass the size test, which allows us to multiply, right? You'd have the 3 paired with the 2. So you can see right there is an example of, in matrix multiplication, order matters. We don't have commutativity, right? Sometimes you can do A times C and C times A, both, but that's more the exception than the rule.